Okay, welcome to lab. And like I mentioned before, we're going to do is, again, just use Elise here, the first part of it to lecture a little bit more to, again, just keep us on track and everything like that. And again, after now, um, after this lecture here, I'll probably, like I said, open up the next experiment, which was officially sort of scheduled for today, which was the basically redox experiment, and that should, you should be able to start working on that one. Again, that one will most likely not be any type of formal report, as we talked about before. Probably the one that you currently have out there, which is the titration one, will probably be your last sort of formal report in terms of what you need to type a report. So this one will probably be more like maybe the buffer one or something like that, where uh, you'll have basically the data sheets and you'll just kind of fill those data sheets in and turn them in and stuff like that. So I anticipate the redox experiment, which again is technically scheduled for today on this schedule, and Tuesday as well. And then we roll into, I think, the electrochemistry experiment, which is also, sort of about galvanic cells and stuff, which we hopefully should get into today. That one's scheduled for a couple of days as well. So both of those experiments, I anticipate being pretty much kind of almost like fill in the blank type of thing. You fill in the sheets and do the pre-lab, post-lab questions, and that will most likely be the reports for those experiments and stuff like that. Okay, so let us continue on here. So we're just talking to make sure again, officially, I don't think in chapter 17 anymore they have this type of stuff. And again, depend on maybe your Chem 50 instructor, you might have went over this or you might not have went over it. So again, I just want to make sure everybody's on the same page in terms of doing these things and you're able to identify things that are being oxidized, things that are being reduced, what's the oxidizing reagent, what's the reducing reagent, oxidation numbers, that you're able to balance these sort of equations because you do need to be able to do that. So we talked about doing it last time here in lectures. So why don't we do at least one more example here and just to make sure. And so why don't you work on this for a few minutes and then we'll talk about it. So in terms of the notes, I think I skipped the next example. So there's an example in between these that I sort of skipped, and we'll just pick it up at this example here. So take a few minutes and work it out, and then I'll come on, obviously, and we'll go through it. And again, just to make sure everybody is at least on the same page in terms of redox reactions and stuff like that. So take a few minutes, work it out. This one we're doing in just acidic solution, so not basic like we did the previous ones. So just acidic solution and see what you come up with. While you're doing it, also, again, see and make sure you can identify correctly what's going through oxidation reduction, which hopefully you can. Also make sure you're able to sort of correctly identify what's the oxidizing agent, what's the reducing agent, and those type of things, okay? So take a few minutes and then we'll talk about this one. Okay, let's see. Let's take a look here and see how we're doing. Oops. Find the one we're at. That one. Okay. All right. So your question is about the previous example, right? So if you want, we'll go through that as well. But let's take a look first at this one here. And again, we want to kind of just break it off into its two half reactions. So that's going to be the two chromiums here together, and our oxalate, which is this guy, and our CO2. And again, we want to maybe figure out what's going on in terms of everybody. So this guy we saw previously was +6. Our chromium here going to +3. So again, if we look at it, we're going from +6 to +3 heading in this direction. So that is going through reduction. Now, when we look at the C2O4, this guy is -2. That gives us -8. And overall charge there is -2. So -8 and -2 is -6. That means each of these are probably +3. While our -2 over here, that's -4. And that would mean that that would be +4 in this particular case. So in terms of our carbon in this case, it's going from +3 to +4, which is heading in that direction, which means it's going through oxidation. So our chromium is going through reduction, and so this would be our reduction here. This would be our oxidation half reaction. Our carbon is going through oxidation. That would also mean that this here would be our oxidizing agent. This guy here would be our reducing agent in that particular case. Any questions on getting all that sort of oxidation states together and everything? All right, so we do want to balance everything. Remember, the first thing you really want to do is balance all the other elements like normal, um, with coefficients besides oxygen, hydrogen. In this case, we do need to do it actually here in the first one. We needed to put a 2 here because we do have 2 of chromiums. And we actually do need to put a 2 here for the carbon as well because of the 2 that is there in addition. Now we can balance our oxygens. So we have 7 oxygens in the top guy. That's going to require 7 waters happening over here. And that's going to mean that we're going to need 14 H pluses on the left-hand side to balance out the hydrogens we added from the water. Now, an interesting happens down here when we look at this one. We have 4 oxygens on the left, but because we put the 2 here for our carbon, that also gives us 4 oxygens over here. So by putting that 2, it actually fixed the oxygens in the second one, which means that the second one actually does not need any waters added in that case. So again, that's why it's really important when you're doing these to make sure that you do go, kind of step by step and follow the steps. Because in this case, by just balancing the carbons, we're actually able to balance the oxygen, so we don't actually need any water. So what we do need to do, though, is add some electrons. So top one, overall charge on the left-hand side in terms of charge is we have +14 for our H pluses and -2 for our dichromate. And that gives us a +12 on left here. Right hand side, we basically have +6 coming from this guy. That means that ran out of room here. I'm just gonna go underneath it. You need 6 electrons added to the left hand side. And that makes sense as well because this is our reduction half reaction, which means that the electrons should be added to the left-hand side of the equation. Overall charge here, our oxalate has a -2, nothing going on the right-hand side. So right-hand side needs 2 electrons to balance it out. Also, again, makes sense because this is our oxidation half reaction. Any questions up to that point? So really at this point, we're ready to add them together, but we cannot add them together until we have really the same number of electrons in each. Top guy has 6 electrons, bottom guy has 2. So really we need to multiply the bottom guy by 3 so that we get the same number of electrons. So I'm just going to rewrite everything a little bit neater. So I'll just put a little line. There we go. So recopying what I got up there on top, 6 electrons plus 14 H pluses plus our C2O7 minus goes to our 2Cr3 plus and our 7 waters. And again, multiplying the 3 to our bottom guy gives us 3C2O4 2 minus 6 CO2 and 6 electrons. Now we're good to go. We got the same number of electrons in each half reaction, so we can cancel them out. And that looks like we will end up with, in this case, 14 H pluses plus Cr2O7 2 minus plus 3 of the C2O4 2 minus. We'll go to 2 the Cr3 plus, our 7 waters, and our 6 CO2. And again, since we want acidic, this hopefully should be balanced. So just to double check, you want to make sure it's balanced both ways. So we do have 14 H's on the left, 14 on the right, 2 CRs on each side. We have 7 oxygens plus 12 more on the left. That's like 19 if I did my math right. Then we got 12 and 7 on the right and 6 carbons on each side. Overall charge on the left-hand side, we have -6 for the oxalate, -2 for the dichromate, and +14, and we're going to go with +6 on that. And on the right-hand side, we have 2 times 3 plus is +6. So again, we're balanced both ways, both in terms of overall charge on each side, which again, it does not have to be 0. And again, the same number of elements on each side is like a normal balancing equation. Any questions on any of those steps there? I would say, in terms of your question, the question is, will the original sort of unbalanced equation be given to you? How can I put it this way? Probably for like quiz or exam purposes, it probably will be. Something like perhaps maybe in the redox experiment that's coming up and some of those, you may have to sort of figure out what's happening based on the experiment that you're doing. So, but it should be something that you probably should be able to figure it out. But for the most part, it will probably be provided for you. So I won't say 100% of the time, but probably most of the time it will be. If not, there should be at least some type of other information that would be provided to you to allow you to sort of figure out what it will be. So for example, in the redox experiment, which is coming up, technically when you do it, it involves, for example, Mn. And depending on the observations that you make in terms of, say, color or maybe a precipitate that you see in the experiment, there'll be like a table that says, hey, if Mn with a +4 charge ends up being like purple, or it ends up being this white solid formed or something like that. So in terms of the experiment, you may have to sort of use some of the observations that you see and a table like that to sort of come up with, okay, I know it started out as MnO4 minus, it maybe became MnO2 or something like that. But in more of a textbook problem or a exam type problem, probably will be given to you. Other questions? Okay, so there was a question on the previous one. So while we're doing it again, just hopefully this is helpful for everybody, I hope. Let's just go through that one and see what we end up with on that, I hope. So even if you know how to do this, hopefully this is good practice or some reminders of how to do it. Again, if you maybe didn't do it so much in Chem 50, which again, like depending on who you had and sort of what you covered, you might not went extremely into detail on it. This hopefully will be helpful. So why don't we just go through this one together here and sort of see what we end up with. So here again, we want to just basically start the same way. We do want to start with the two guys that are related to each other. So we do have our Mn2 plus, our MnO2, and then we would have our peroxide here, our hydrogen peroxide, and we would have our H2O. Now, in this particular case, to figure out sort of what's happening, this guy obviously does have an oxidation state of +2. The oxygen here is -2 for this guy, which means we should end up with a +4 for the Mn. So in this particular case, we're going from, again, if you just simply want to figure it out using sort of the number line, you're starting at +2 and you're ending at +4. So you're moving in this direction. And again, when you move in that direction, you're going through oxidation. And that would mean this would be our oxidation half reaction. And by default, this would be our reduction half reaction. Now, to see sort of the reduction part of it, let's take a look and see what's actually happening. The oxygen here is actually that peroxide, since this is hydrogen peroxide. So the oxidation number of this oxygen is actually -1. And the hydrogen here is still +1. And again, because that is really the peroxide polyatomic ion. When we come over to the water, the oxygen is actually -2 here and is +1. So in terms of the oxygen, you can see the hydrogen is not really changing, but in terms of the oxygen, it's actually starting at -1, which would be here, and it's actually ending at -2, which is moving in this direction. So it is actually the oxygen here that is going through the reduction aspect of it. And again, most of the time we do see oxygen, it is going to be, it is going to probably be that -2. But again, here obviously is something you can identify it as a peroxide. You know, hydrogen peroxide is a common one. Sodium peroxide sometimes pops up a lot. And again, because it is peroxide, you typically will be able to figure it out by the sort of extra twos that you would see. And what I mean by that, for example, if you had, just taking a moment to talk about that, if you had, for example, sodium, right? And you're like, okay, is it hooking up with, oxygen, or is it hooking up with peroxide? The difference is in the two formulas, if you look at it, they're both going to have the 2 there, right? For this. But for the sodium peroxide, you will have that extra 2 that basically will be in the formula. And the one on the left here would be -2 in terms of oxidation state. This guy here would be -1 in terms of its oxidation state. So again, that sort of 2, or that extra 2, if you want to think about it, sort of does pop up in those type of situations. And that's sort of how you could sometimes distinguish if you're dealing with sort of just the oxygen or the peroxide. Usually you'll have kind of like an extra 2 somewhere in there. So when we do this, we do want to sort of follow the same sort of things that we did before. We want to balance everything other than oxygen and hydrogen, again, with normal coefficients. So on the top one, we have 1 Mn on the left, and on the right, we do have 1 Mn as well. So it's okay in terms of how many we have. And that pretty much just leaves us oxygen. So let's start with that. Top guy, we have 2 oxygens on the right, which means we are going to need 2 waters here on the left. Because we added 2 waters, we would have to add our 4 H pluses. Now, when we go to the bottom one, we have 2 oxygens on the left, 1 on the right. So we do need to add 1 water. So because this is really water as well, you actually can just put the 2 in front if you want, or you can write another H2O, whatever you want to do. If you decide to put the 2 in front like I did, you do have to keep in mind that technically speaking, you're just adding 1 water, right? Which means to the left-hand side, you basically only need 2 H pluses. So again, you don't want to add 4 H pluses because technically speaking, you're only adding 1 water. All right, at this point, we could do a little bit of balancing in terms of overall charge. We could add our electrons. And excuse me, the top half reaction, we have an overall charge here of +2. Right-hand side, we have an overall charge of +4, so we're adding negative electrons. Top guy needs a couple of electrons, going to get us to +2 now on both sides. Also, again, makes sense since this is the oxidation, we see our electrons on the correct side of the half reaction. Looking at our bottom one, we got +2 on the left, and we got 0 here on the right. So we do need to add a couple of electrons over here on the left-hand side. Also makes sense because this is our reduction half reaction. We do see our electrons on the correct side. And if I'm not mistaken, I think we're good in that in terms of electrons. So we actually could add both of these together and we could cancel out whatever is the same on opposite sides of the arrows. We also can reduce down. So looks like for sure our electrons are going to cancel. And in this particular case, if I'm not mistaken, it looks like perhaps our H pluses could cancel a little bit. So we will have 2 H pluses. And I think that's it in terms of canceling. So we're going to end up with Mn2 plus H2O2 on the left-hand side of the arrow. And I also, by the way, I didn't cancel them, but we could also cancel out the waters, which is good because I didn't write it. Water here and water here will cancel. Now on the right-hand side, we will end up with MnO2 plus 2H pluses. And excuse me, at this point, we should be balanced in terms of acidic solution. If we just to verify that we are, if you look on the right-hand side, you will see 2 H's, left-hand side 2 H's, 2 oxygens on each side, and an Mn on each side. Overall charge on the left is +2. Overall charge on the right is also +2. So again, if we were balancing the equation here, we would be done in terms of acidic. But since we're doing basic, what we're looking for now is we need to add OH minus to both sides. And again, the OH minus that we add is going to be equal to our H plus. So here we would add 2 OH minuses to the right and a couple of OH minuses here to the left. As we talked about before, in this particular case, these are going to combine to make 2 waters. And that's going to leave us 2 OH minus plus Mn2 plus H2O2, going to give us MnO2 plus 2H plus and a couple of waters. Yeah. And again, if we didn't screw up anything here, hopefully we didn't. We should still be balanced, obviously, in terms of charge and also elements. So left-hand side, 4 oxygens, right-hand side, 4 oxygens, left-hand side, 1 Mn on the right, and 2 hydrogens on the left, and 2 on the right. Overall charge on the left-hand side is, what do we got there? We got 0. Overall charge on the right-hand side is +2, and clearly something did not go right there. So what did I miss there? I feel like see here real quick. Oh, I wrote the two H pluses there. That would not be good. All right, that became part of this. So my bad. I apologize. Try that again. Now we're better. There we go. So again, we should hopefully be balanced. Let's try this one more time here to make sure. We do have 2 oxygens, and 2 gives us 4 on each side. And we do have 4 hydrogens on each side. We have 1 Mn on each side. Overall charge on the left is 0. Overall charge on the right is 0. Yeah, thank you. I forgot I already combined those and brought it down. Thanks. That's good. It wasn't bad all the way down, right? So that's good. Thank you. Yeah, so the balanced one should look like this. I apologize about that. And again, that's also a good way. Obviously, you see, you can just make a simple little mistake like that. And if you, again, check yourself at the end, you do know that something did definitely go wrong like I did right there. Obviously, it, again, should be balanced both ways in terms of elements and charge. And you hopefully it will just be something simple like that. You could just cross it out at the end and not have to go all the way back. Any questions on balancing these guys, identifying redox reactions? What's the oxidation reduction? What's the oxidizing agent and reducing agent? So again, in this case, the reducing agent would be this guy here. And our oxidizing agent would be this guy here. Remember that the reducing agent and oxidizing agent is always found on the reactant side. And you should really identify them, by the way. That's why we're talking about this for a little bit more detail, I guess. You should make sure you do identify it. So for example, if you're asked what's like the reducing agent or the oxidizing agent, and you just write Mn, you know, it sort of doesn't really imply what you're talking about. You know, I don't know if you're maybe thinking about this guy or which guy. So when you're asked those questions to identify the reducing agent or oxidizing agent, do be pretty specific, like, hey, it's this guy, you know. The other guy is, you know, this guy and stuff like that. So that is clearly understood, again, that you know which one is which. Any questions on balancing those there? Okay. All right. So obviously, again, you should be able to do these. You do need to be able to balance those guys out. Like I said, in acidic are basic solutions, and obviously be able to identify all those things, the things being oxidized, the things being reduced, and the oxidizing agents and reducing agents as well. So now let's get into really this chapter here, which is electrochemistry, and we're going to talk about galvanic cells. And really, galvanic cells are really just oxidation and reduction reactions or redox reactions that are taking place. And this is a basic sort of galvanic cell that you could build in the laboratory. And let's talk about some of the components here that make up a galvanic cell. And a galvanic cell basically has one side, for example, in a beaker, another side in a beaker. The 2 beakers are basically connected together. And on the left-hand side in this picture, this is the side which is known as the anode. And the anode side of a galvanic cell is where oxidation occurs. And again, oxidation is going to mean that we're going to lose electrons. So that's what we see here. From this electrode, the electrons are going off through the wire, and it will give us some type of voltage, right? And electrons will come down to the other side of a galvanic cell, and they will travel to the side which is known as the cathode. And the cathode side is basically where reduction takes place, and that's where it gains those electrons. So we typically in a galvanic cell will have a solution, and in the solution part, it typically will have the ions of the solid electrode. So usually there's some type of solid electrode that's used. And in this case, it's zinc. So typically in the actual solution, we would have, for example, zinc ions that are floating around in the solution. And as the reduction occurs, the oxidation occurs, the zinc goes from solid state to basically an aqueous state. And that's usually what ions are. They lost their electrons. So it's going from the solid state to the aqueous state, and those electrons are being lost. So basically the zinc guys here are starting on this solid electrode, and they're basically jumping off into the solution as this oxidation process basically occurs. And what happens on the other end is we typically have a similar setup. We also typically would have a solid electrode on the other end. And as those electrons come in, we would also have a solution that contains ions from that electrode. So here we have a copper electrode, and we have copper ions in solution. So as those electrons basically come in, they're going to hook up there with our copper 2. And essentially what's going to happen is the copper 2 is actually going to come out of solution, if you want to think about it, and kind of plate itself, if you will, on that electrode. And that's what we see here on this half reaction here. The copper 2 ions in the solution will basically gain the electrons and become solid in this case. And as those electrons are basically traveling from one side to the next, they can be used to do some type of work. And this is essentially kind of like what a battery sort of operates on. It basically does this sort of redox reaction. Electrons go out, powers your device, right? You look in the battery compartment, there's wires and stuff like that, right, where you put your batteries in. And again, obviously those electrons are used to sort of power, your device and so forth. And on the left-hand side, we see our anode, which is our oxidation half reaction. Again, we see electrons on the product side, reduction half reaction happening here with our copper, and electrons on the reactant side. And we basically could add both of these half reactions back together. And if you do, you will get that overall reaction that's taking place, which is what we see on the bottom of the screen there. Again, when we would add these together, electrons would cancel, and that leaves us the overall reaction that we see there, which is what is sometimes referred to as the net ionic equation. It basically is sort of what is happening here. It's not necessarily a net ionic equation, maybe like you usually envision it when we do double displacement reactions, but it really is showing you that the zinc here is going from 0 to +2, copper going from +2 to 0. So again, if you look at that little number line, zinc going from 0 to +2 being oxidized, and copper going from +2 to 0, which is being reduced. It means in this particular case, our zinc, which is being oxidized, is our reducing agent, while the copper here, which is being reduced, is our oxidizing agent. Now, there's also another thing that usually we'll see in a galvanic cell, which is this salt bridge. And the salt bridge, remember, is salt is really just an ionic compound. And it usually will contain some type of ionic compound like potassium chloride, sodium nitrate, something where there's like only a positive and negative charge. And the purpose of this is to sort of keep this reaction going in that sense. And what I mean by that is if you think about what's happening in this reaction, right, you are basically on this side dumping into the solution a bunch of positive charge, right? So as those ions lose those electrons, all these ions now with the positive charge, right, is going into the solution and building up the positive charge. While over here on the other side, you're basically taking out all these ions that are positively charged. So what you're sort of building up on this side is more of a negative charge. And at some point, what's going to happen is if you did not have, for example, the salt bridge in there, there's going to be sort of a complete buildup of like positive charge on the left hand side in this picture, negative charge on the right hand side, and basically it will basically stop working, this cell. And what allows it to work is there's sort of an overall, if you want to think about it, positive difference, if you will, potential difference from the left hand side to the right hand side, that's helping those negative electrons want to come, to the right hand side. And again, if you sort of have just the salt bridge out of the picture, as this thing is running, eventually what's going to happen, you're going to build up this negative charge and more negative charge on negative charge. So these negative electrons, right, are going to decide, whoa, that's way too negative. I'm going to U-turn, and I don't really want to go in that direction. So what basically sort of a salt bridge does, as you can see here, that's why we see our positive potassium heading this way, right, to kind of counteract that buildup of negative charge on that side, while we see our negatively charged chloride ion heading in this direction, again, to counteract the big buildup of positive charge on that side. And by having that salt bridge there where those ions basically could kind of come in and prevent this sort of overall buildup of positive and negative charge on each side. And what that allows it to do is allows the cell to sort of continuously run and without that effect happening. So what you really need in this cell is, again, that sort of charge difference where the electrons really want to be pulled towards the cathode side. And you want it to be a little bit more positive on the cathode side than the anode side to bring those electrons towards it. And again, without that salt bridge there, you're going to get basically the opposite effect sort of happening. You're going to build up an incredible amount of negative charge on the right-hand side here. And that's definitely not going to allow those electrons basically to come to the other side. Any questions on that? So you do need to know what a galvanic cell looks like. You do need to be able to draw one. You need to know what the anode looks like, the cathode looks like, what happens on the anode side, what happens on the cathode side, what the salt bridge purpose is for. Any questions on that? Okay. So when we talk about sort of galvanic cells, as I mentioned before, there really is sort of what is sometimes referred to as that potential difference between the anode and cathode. And, just kind of simply thinking about it, you can think about the cathode side as perhaps being a little bit more positive. And that's going to, again, sort of pull those electrons from the anode to the cathode as, again, opposites attract, right? So they're going to be attracted to the other side. And one way that we sort of represent that difference in potential is through basically these three sort of things. And ultimately, when you're asked a question about these things, they're ultimately kind of the same thing. The cell voltage is a volt is 1 joule of work per coulomb of charge that's transferred. And that's what basically this conversion here, a volt is 1 joule over a coulomb. Coulomb is basically a unit of electrical charge. You may also sometimes be asked to calculate the EMF of a cell, and that's the electromotive force, or you may be asked to calculate the cell potential. So ultimately in a question, if you come across it and it asks you to calculate the cell voltage, if it asks you to calculate the cell EMF, or if it asks you to calculate the cell potential, for the most part, they're pretty much all asking you to calculate really the cell voltage, right? And that's sort of what we see here. In a good cell that's, sort of a spontaneous process, you will see usually a positive voltage, and that's usually really good. That means it's sort of spontaneous. So for example, in that picture, probably the zinc and copper sort of cell, when they hook it up together, they got a cell voltage of 1.1 volts. And again, a positive voltage is usually pretty good. So if we look at the cell reaction as we see, and if everything in terms of concentrations are all 1 molar. We can also represent a reaction by what is sometimes referred to as the cell diagram. And the cell diagram is actually this thing on the bottom here. And let's sort of talk about the parts of the cell diagram. This cell diagram is basically a representation of this chemical reaction that's taking place. And the first thing that we typically always sort of write in a cell diagram is we go from the anode to the cathode. So in this reaction that we saw earlier, again, the zinc is going from 0 to +2, being oxidized. And since it's being oxidized, it is the anode. While our copper is going from +2 to 0, it is being reduced, and it would be then the cathode that's happening. And that's always the way sort of a cell diagram is set up. On the left-hand side is the anode, right-hand side is the cathode. And in general, when you look at a cell diagram, in general, the first thing listed here is typically the reactant side, which is what we see here. The second thing listed is usually the product, which is what we see over here. And there's usually one line between them. So this one line between them kind of separates the reactant and product side of the anode. Because this has a concentration, you will sometimes see the concentration also written into the cell diagram. If it's a gas, you may also see pressure written in there. And usually remember, when we talk about standard conditions, like we talked about in thermodynamics, pressure is 1 atmosphere, right? Molarity is 1 molar. So we will see some of that sort of thermodynamic stuff come into play here as well. But essentially, same sort of thing about standard conditions. 1 atmosphere for gases in terms of pressure, 1 molar for solutions in terms of molarity, and usually temperature is 25 degrees Celsius. Now, the 2 lines that separate the anode and the cathode is what represents the salt bridge. So this guy here represents the salt bridge, which physically, if you look in the picture, right, is the thing that separates your anode, right, to your cathode. So same thing here in the cell diagram. It is the thing that separates the anode side to the cathode side. And on the cathode side, it works the same way. You have your reactant first, which is what we see over here. And since that's aqueous, they did include the concentration. And then you have your product, which we see over there, also separated by 1 little line as well. So sometimes in problems, you may not be given a actual chemical reaction, or like we have it above. You may be given the cell diagram, and you need to basically be able to turn that cell diagram again into an equation. So if we were working backwards from the cell diagram, we would see our zinc on our reactant side. We would know our zinc would then end up on the product side on the other side. Then going to the other side, we see our copper would be a reactant, and our copper would be a product on this side. So again, from the cell diagram, you could basically get the equation. And like I said, sometimes you will see some other stuff in that cell diagram, and we'll see it in a second or so, that do pop up in there, and we'll sort of talk about those things as well. Questions on how to write a cell diagram, or how to go from a cell diagram to an equation. And obviously, if we were going from the equation back, this is a reactant and then our product that matches, right? So you go reactant, product that matches, reactant, and product that matches going the other way. So again, you can sort of go both ways with those things. Now, if we look at this cell here where we hooked up, in this case, a zinc electrode. And in this case, this is a hydrogen electrode. And in this case, on the left-hand side, this is our anode. So we do see the electrons traveling away from the anode towards our cathode on this side. And the hydrogen electrode is the cathode. Now, the hydrogen electrode is really the hydrogen gas. So obviously it's a gas, which means you don't really have a sort of solid version, say, of hydrogen that you could put on there. So sometimes what will happen when you have either an anode or a cathode where you don't necessarily have a solid electrode like you have over here, they will sometimes use some type of other metal as sort of the physical electrode that's being used in the experiment. And that's why we're using the platinum electrode here. Sometimes people will use graphite, right, which is basically carbon. So sometimes people will use some graphite or other sort of guys as the physical electrode to build the cell. And that's very common when you have something like hydrogen gas or gases that are involved. Again, you need some type of physical sort of electrode basically to connect both sides. Otherwise, if you had nothing physical on the right-hand side, these electrons would like fall, probably not fall, but like, whoa, where am I going? And maybe miss the beaker, right? Because remember, those electrons do sort of follow the wire all the way down. So you need some type of physical thing to allow them to actually get to the other side. And again, when we have something like hydrogen gas here, something like the platinum electrode is used. But because hydrogen is a gas, we would not really talk about it in terms of concentration, but we would talk about it in terms of pressure. And when we look at this reaction, what we see is the zinc, in this case, which is our anode, is going through oxidation. And by default, it means the hydrogen is actually going through reduction. And what's happening there is hydrochloric acid means there's a bunch of H pluses floating around in here. So as those electrons come in, they're going to gain the electrons, and we're going to actually form hydrogen gas. So a little bit different. You won't get a solid that's formed here. You will get those bubbles that we see starting to form, which would indicate that we are making hydrogen gas in this particular case. So when we look at it, our oxidation is our zinc going from 0 to +2 in this case, becoming more positive, right? Moving in that direction. While when we look at the hydrogen, it's going from +1 to 0. So starting at +1 and heading to 0, which means it's going through reduction in this case. Oxidizing agent would be the H+. The reducing agent would be the zinc in this case. And if we look at our cell diagram for this, this is our anode, separated by the salt bridge to our cathode. And when we look at the cell diagram that's written for this particular one, we do see a few different things in it, but it's the same pattern. If we look, this is our reactant, this is our product. So if we come down here, there's our reactant, there's our product. And same thing over here. This is our reactant, which is the H+, which comes from the HCl. And this is our product, which is the H2. But we also see a extra thing sort of in here, which is the platinum electrode. And again, that is typical in the cell diagram. People will include, the physical electrode. They may even say something like graphite. They may say like the platinum is here. And again, that's just to indicate that one of our electrodes here is basically a gas. So this is sort of the physical manifestation of that electrode. The other thing that we also see is instead of a concentration for the H2, we see a pressure that's also included in the cell diagram as well. So same thing as we talked about, anode to cathode, reactant product, but again, we'll have some pressure involved, and we will also see the kind of physical electrode being included sometimes in the cell diagram. The physical electrode, as you can see, though, the platinum not included in any of the sort of reactions, if you will, but it does find its way sometimes into the actual cell diagram. Any questions on that? Now, this hydrogen electrode is actually a sort of a special electrode, and we're going to talk about it here right now. When we talk about sort of half reactions that occur in these sort of redox reactions that involve electrons, we sometimes talk about the standard reduction potential. And the standard reduction potential is sometimes abbreviated as SRP, standing for obviously standard reduction potential. And it is sometimes also abbreviated in a table as E naught. And that's the voltage that's associated with the reduction reaction at an electrode under standard conditions, which is why we have the little knot like we saw in thermochemistry. Again, that little knot means standard conditions, 25 degrees Celsius, 1 atmosphere for pressure, 1 molar for concentration. Now, just like anything else sort of in chemistry, at some point they needed a standard basically to compare everybody to. And for standard reduction potentials, they chose basically the hydrogen electrode as that standard to compare everybody to. And it's sometimes referred to as the standard hydrogen electrode, sometimes referred to also as SHE for standard hydrogen electrode. And they sort of arbitrarily assigned the hydrogen electrode a SRP value of 0. And basically, what we see here is the half reaction for hydrogen, and it has an E value of 0. Now, an important thing to keep in mind when we go through these guys is we are looking at what is known as SRP values, which are standard reduction potential, which means we're going to see a table shortly. And in that table, every single reaction will be written just like this one. And what I mean by that is this one is written as a reduction reaction. So when you quote an SRP value or see an SRP value, it is always for that half reaction that is written as a reduction half reaction. And that's going to create some issues a little bit later on that you need to be aware of, because as we know, what we're really dealing with here are redox reactions, which means in addition to the reduction reaction, there is also obviously the oxidation half reaction. So you do have to do a couple of things, which we'll talk about. But essentially what they did is they took this standard hydrogen electrode and they basically hooked up galvanic cells and hooked up other things to it. So if we look at this, where they take the the standard hydrogen electrode and they hook it up to zinc in this case. So again, zinc here is our anode. Our hydrogen electrode is our cathode. And if they hooked it up, what they got was a cell voltage for this cell of 0.76 volts, which is good. That means electrons are really running from the anode to the cathode side. And they use this equation here, which is one equation that you could use to calculate the standard EMF of a cell. And it is E of the cell equals E of the cathode minus E of the anode. Now, when they did the cell, they saw that it was 0.76 volts was the cell voltage. In this case, our cathode was set up as our hydrogen, which has a value of 0 volts, which means they were able to figure out that the E of the anode, in this case, was minus 0.76 volts. And they're able to figure out that the E of the cell for the zinc part in this case would be our, would be our 0.76 volts. And what that means is the SRP value for zinc would be minus 0.76 volts. Now, let's just take a moment to talk about this equation here, which you could use. And again, it may not make sense right at this moment, but we'll see it a little bit later. So just to take a moment, if you decide to use this cell, this equation here, which is our cathode minus our anode, you typically will get these values from a table, an SRP table. And if you do, you technically would leave all the signs that you see in the table alone. And what I mean by that is, technically speaking, when we see this table, it is all reduction reactions. But really, one of the reactions, as we see here, is actually an oxidation half reaction, which means, technically speaking, you should change the sign that you find in that table. But you do not want to do that if you use this equation where you subtract. If you use the equation where you subtract, you should use the signs that you find in the table exactly how you find them. If you decide to add, which you could do as well, so here's sort of another version of this equation. You do need to change the sign of your anode that you find in the paper, in the table. In this equation, if you subtract, you do not change the sign. And again, it may not make a lot of sense right at this moment, but in a few slides, hopefully it will. So just keep that in mind, that you will see this equation in a couple different versions, but when you add, it assumes that you change the sign yourself. When you subtract, you don't change the sign because the equation will do it for you. So let's continue on. And again, I'll show you sort of an example of that in just a second. Now, if they took the standard hydrogen electrode and they hooked it up now in this case to, excuse me, copper, we also see a couple of important things. In this case, the hydrogen is actually the anode and the copper is the cathode. So that brings up a really good point, that pretty much anything can be either an anode or a cathode. It just means that when you hook it together, it may work or it may not work in terms of voltage and stuff like that. Or you may get negative voltage, which means you essentially just need to flip them around and stuff like that. But things can be an anode, things can be a cathode, and it doesn't really matter. In certain cases, it may work. In certain cases, it may not work. But here, as we moved over and we wrote our cell diagram, we now see our anode is different, and this guy is our cathode. But same idea, this is our reactant, this is our product, this is our reactant, and this guy is our product that we see here. So putting it into that equation where they're subtracting, they took the 0.34, they had our value of 0. That tells us that the copper's SRP value will be 0.34 volts. So this is a way, again, that they were able to basically come up with SRP values for everybody. They use this sort of standard hydrogen electrode as a standard to compare everybody to, and kind of simply, if you will, built all these galvanic cells and measured the voltage. So let's take a look at this table here. So this is a table, not from your book, but you have a similar table. I almost want to say in the chapter. It might be in the back of the book as well. But these are all, if we look at this table and we look at each of these reactions, these are all SRP values. And that means that these are all reduction reactions. So when you go to an SRP table, every single reaction that's listed along with its E value are representing the reduction reaction only. So here's a whole bunch. Here's another table. Let's talk about sort of this table and sort of the things that we do with these values. Obviously, this table would be provided for you, but obviously in a book type problem or something like that, you may need to, refer to a table to look it up and stuff like that. First off, the E that is written is for the reaction as written. And as I mentioned, when you do look at this table, our A table, it is always going to be the reduction reaction, which means you will have an oxidation reaction that is basically the opposite of that reaction. Excuse me for 1 second here. Now, when we look at this table here, sometimes you may be asking yourself, what is going to be the cathode? What is going to be the anode when you're just given information about building a galvanic cell? So there's a lot of questions where they'll just say, hey, we just going to build this galvanic cell out of these two things. Which one's going to be the anode, which one's going to be cathode. So the second thing here is what you could use to help you along with that. The more positive the E value that you see on the table here, the more tendency that thing will be reduced. So what does that mean is if something is more likely to be reduced, does that mean it is the anode or the cathode? So if something is more likely to be reduced, what that means is it is going to be the cathode. So you can use these E values to basically determine in a situation where you're not given any information about how the cell is actually put together, but you're just told basically, hey, you're going to put these two things together. You can use the E value that you find on here, the SRP value, to determine the one that is more positive will be your cathode. Now, the other thing that's important is the next one. Each of these reactions are reversible, which means technically speaking, let's just kind of pull one out here and take a look at it. So let's see here. We'll do the lead. We look at the lead. Of course, this is the smallest table known to man, right? 2 electrons go to lead that's solid. And if my eyes didn't fail me there, the E value that should go with that should be minus 0.13 volts. So this is written as a reduction reaction. If I needed the oxidation reaction, it would be the same reaction, just reversed, right? It would be the Pb that goes to the Pb2 plus the 2 electrons. Now, if you reverse this reaction, what's going to happen to the E value is for this reaction, it actually would become positive 0.13 volts. So the oxidation half reaction can be found on this table, but it is basically the reverse of what you see on that table. And technically speaking, if you write the oxidation half reaction, you should change the E value. And that's where we come into play that equation that we saw earlier where it was cathode minus anode or cathode plus anode. So let's talk about those last point here, and we'll go back and sort of show you the difference between those two equations. Now, the last thing that you do is when we do these redox reactions, sometimes we do need to make sure that we have the same number of electrons in each half reaction. So sometimes, as we saw earlier, that does require us to multiply by a common number. And unlike thermodynamics, where, for example, we have, A plus B goes to C, delta H is 2, and I decide I'm going to multiply this entire thing by 2. And then my delta H would then just get multiplied by 2 as well. Or with our K value, if we multiply by a common number, we may take it to the exponent. When you have to multiply a half reaction by a common number to get yourself to the right number of electrons before you add them together, you can multiply by as many big a number as you want. The E value, the SRP value, will not change. So for example, if I need to multiply this equation by 4 to get the right number of electrons, that would give me 4 Pb2 plus 8 electrons, gives me 4 of my solid. In terms of my E value, it will remain exactly the same. So if you multiply by a common number, it will not have an effect on the SRP value. So that's an important thing to keep in mind. And the two other really important things to keep in mind here from this slide is if you're trying to determine which one's your anode and which one's your cathode, you will take the one that is more positive, and that should be your cathode, and the one that is less positive would be your anode. But an important part of that is if they actually do give you the reaction that's taking place, or they do tell you you're reacting this guy with this guy, you do need to follow those reactions that are given to you and see what's being oxidized and what's being reduced. So in a case where they actually do give you the reaction, you need to see who's being oxidized, and that will tell you which one will be your anode, and what's being reduced will tell you which one's your cathode. But if they don't give you any of that information, you can use the SRP value. We see that the more positive value is up here at top, and that is where we get an increase in the oxidizing agent. So this is the better oxidizing agent up on top. And that's because the oxidizing agent gets reduced, and this is the most positive. So those guys should be your cathodes. While down here, this would be your better reducing agent. On the bottom of this table, these are more negative. So more negative is going to be oxidized, or your anode, and it would be your better reducing agent. All right, any questions on that? Let's go back and sort of just kind of maybe show you the difference between using those two equations, which is really kind of the same equation. So let's take a look at just a cell that we built, right? And let's take a cell that we built from, let's just pick randomly two things. Let's do cadmium. And let's do, we'll do the one right underneath so we don't have to dig too far. Let's do iron. So cadmium and iron here. And that would give us this guy from this table here. And it would give us, obviously, this guy from this table here. Okay. So if that is all that is given to us, is that we're going to build a cell out of those two things, we would go to this table and we would find those values. And what we would be looking for is, in this case, because we're not given any information about, what is happening, we can use our SRP values that we see. And what we see is when we look at our cadmium, it is going from cadmium with a +2 plus a couple of electrons to our solid cadmium, and it has an E value of minus 0.4 volts. When we look at our iron, it's going from iron 2 plus a couple of electrons going to our solid iron, has an E value of minus 0.45 volts. So in this particular case, we can use those E values to determine which one is our cathode and which is our anode. So I'll give you a second for you to decide which one you think is your cathode and which one is your anode in this case. So if we look at it, hopefully you came to this decision. The one that is more positive is our cadmium in this case. Barely, they're both negative, but this guy technically would be more positive, right? Closer to 0. So based on the E values, our cathode should be our cadmium as it's more positive. Our anode by default would be our iron 2 in this particular case. So that means, technically speaking, the anode, which is our oxidation reaction, is really not the reaction that is being shown here. It actually should be the reverse reaction. So it actually should be the iron going to iron 2 plus 2 electrons. And that guy technically would have an E value that then becomes positive 0.45 volts. And that would be the correct E value for this reaction, written as a oxidation reaction. Our cadmium would be exactly the way it's written, since it's our cathode. And its E value would remain the same, minus 0.4 volts, which, if we add these reactions together correctly, our electrons would cancel, and we would end up with our iron plus our cadmium with a +2 charge goes to our iron with a +2 charge and our cadmium. And if we were to write our cell diagram for this, we would have our iron, right, which is our reactant, to our iron here, which is our product, our salt bridge to where we would have our cadmium and our solid cadmium, right? So this would be our anode. This would be our cathode. I didn't include the molarity, but you could include 1 molar on each of those guys and assume it's good. Now, what this has to do with that formula that we saw earlier of E of the cell equals E of the cathode minus E of the anode is, if I wanted the E of this cell, I could use this equation just the way it is, which means when I would put it into this guy, I would take my cathode value, which is over here, and go minus 0.4 volts, minus my anode value, which is right here. And here we would actually not change the sign. And the reason we would not change the sign is because of the minuses here. The minus is here to actually change the sign for you, which is what we did right here, right? So technically speaking, for our anode, it should be the positive value. And that's really why the negative is in that equation. It's there to basically change the sign for you. And what we would get is a cell voltage of 0.05 volts, right? Now, why I said you could actually do this guy like this, E of the cathode plus E of the anode, is if you decide yourself to change the sign, which technically speaking is the correct E value for this equation, which is really what's happening here, you should not subtract those values, but after you change the sign of your anode, you should add them together. And if you did that, what you would get is plus 0.45 for our anode that we changed the sign, plus minus 0.4 for our cathode there. And you will end up with the same answer as you get above. So what I would recommend in terms of this equation is to choose a method and stick with it. So if you choose the method where you're going to subtract, then when you go to the table, even though technically speaking and correctly speaking, the anode reaction should be reversed and the sign should be changed. But if you decide not to change the sign that you find in the table for the anode, you should subtract. If you decide, I want to just make sure everything is correct all the way through, I'm going to change the sign of the anode, then what you need to do is actually add those values together. What you don't want to do is change the sign and then subtract them, because then you're just going to undo, what you just did. So I hope that sort of makes sense. So you will be going to this table to find values. Again, sometimes those values, at least one of them will always has to be reversed, which is your anode. And again, you could choose either to leave the sign like you find in the table and subtract, or you can change the sign and add. But again, I personally would probably choose one way and stick with it, so you're not kind of mixing it up as you kind of go back and forth. And I show you both ways because people will do it sort of both ways. So I want to say probably in your lab that's coming up in the introduction, I believe she changes the sign on the anode and then she adds them together. So I don't want you to get confused why we're talking about subtracting when she's adding, but she's adding because she herself changed the sign for the anode, which is perfectly fine and actually more correct because it does represent the correct value. And then she's going to add them together. But again, I think your book might show it to you in the subtraction way. And I personally will oftentimes do the subtraction way sometimes. And there's nothing wrong with the subtraction way. Again, the key is you just can't change the sign of the value that you find in the table. All right, so I hope all that muttering there makes sense. All right, let's take a look. Yeah, typically you do in the cell diagram. Typically you would include the molarity. I didn't here because I was a little lazy when I was writing it. I was trying to squeeze everything in. But typically you should probably include the molarity. So something like this probably would be 1 molar here. It would be 1 molar here as well. And again, if you had something that was a gas, you would include probably the pressure as well. Other questions on that? All right, so let's maybe look at an example where we could actually kind of put all this into sort of play here, I hope. Perfect. So why don't you take a moment here and calculate the standard EMF of this cell. Basically, what is the cell voltage if you make a cell with cadmium and chromium? These are the SRP values and the equations that you would find from that table. So why don't you take a second, and while you're here, why don't you also write the balanced equation? Why don't you also write the cell diagram for it, just to make sure? And why don't you also identify which is the anode and which is the cathode? And then obviously calculate the cell voltage. Yeah. All right, so why don't you take a couple of minutes and work through all those and see what you come up with, and then we'll talk about it. Okay, so let's take a look. So again, in this case, we're not given any information in terms of how the cells actually put together. We're not given an overall reaction or anything like that. So we can use our SRP values, which you would find from the table, to help us decide that. And what we see here is the cadmium here is more positive, which means this guy should be our cathode and this guy should be our anode. So if you wanted to write the balanced equation, technically speaking, our cathode would remain the same with an E value of minus 0.4 volts. Our anode is the oxidation one, which technically means it would be reversed, which means it would be Cr going to Cr3 plus and 3 electrons. E value would change technically for that guy to 0.74 volts. If we want to add them together to get our overall reaction, we do need the same number of electrons. So we would have to multiply the top guy by 3. We would have to multiply the bottom guy by 2. And if we do, that will give us 3Cd2 plus 6 electrons, gives us 2Cd, or 3 CD. And as I mentioned before, when you multiply by a common number with the SRP value, it actually will not affect the SRP value. So the SRP value remains the same. We'll do the same thing for the bottom. That's going to give us 2Cr, no plus. And 3 goes to 2Cr3 plus and 6 electrons. Same thing on the bottom here. Multiplying the bottom by a common number will not have an effect on the SRP value. Electrons are going to cancel, going to give us a balanced overall reaction of cadmium with a +2 charge, plus 2 CRs. Going to go to 3 cadmiums over here that are solid, plus 2 Cr3 pluses. Any questions on how to get to the balanced equation or deciding cathode and anode? Now, if we were to write our sort of cell diagram here, it would be our cathode, right? Which, I'm sorry, our anode to our cathode. And our anode is the chromium. So we would have the chromium, right, to our chromium with a +3 charge. We can get it to right there. And again, we'll just assume it's 1 molar, which it is in this case, actually. And then going to go to our cadmium, which would also be 1 molar, and our cadmium, which is solid over here. So again, our anode to cathode. Any questions on that? Now, to get to the E of the cell, here again, you do have 2 options. You could go your cathode minus your anode. And again, if I'm subtracting, I'm not going to change the sign. So that's going to give me minus 0.4 volts minus a minus 0.74 volts. And that's going to get us 0.34 volts as the voltage here. And that's good. It's actually a positive voltage, which is very good as well. Alternative to that is if you change the sign like we did here, you can simply just add those numbers together with the sign that's already been changed, and you will end up with this same cell voltage of 0.34. So again, it really is your preference. If this was a problem where you just needed to figure out the cell voltage, you can go cathode minus anode from the table. Don't have to worry about figuring everything out. No, it wouldn't be wrong. You can actually put the coefficients in if you like. So this was a 2, I think, right? And a 3 if you like. It's okay to include them as well if you like to. Sometimes they will be left off just to keep it a little bit more simple and stuff like that. But for me, it would be fine if you include them in there. It would be okay. But you can leave them off if you like as well. Other questions on that? So hopefully you're getting the idea of, again, the idea between the adding and subtracting. And again, it really is sort of your option as to which way you want to do that. Why don't we look at maybe one more here? So this galvanic cell, we want to calculate the EMF of this guy, or the cell voltage. So why don't you calculate it and see what you end up with here? Okay, so in this one, we're just looking to calculate the cell. We didn't really ask about balancing everything, but you could if you wanted to. In this case here, we're not given really, again, any direction in terms of how this reaction is going to take place. So we can look at our E values here, our SRP values, and here we do see that the 0.8 is more positive, which means this guy should be our cathode, and by default, the other guy would be our anode. So really, if it was a question like this where you're just calculating the cell voltage, you could just plug and chug right into this equation. And again, here I'm going to subtract, so I'm not going to change the sign. So my cathode is minus, it's 0.8 volts. Minus our anode, which again, that is why the minus is there, basically to change the sign for us. And that will get you a 0.8 minus a minus 2.37, going to give you a cell voltage of 3.17 volts. By the way, a positive cell voltage is good. It means reaction is probably spontaneous. Ultimately speaking, in terms of the reaction, we are looking at this for our cathode. We're going to reverse it for our anode. We would need to multiply them both together here by 2. Our E value for this guy would be 0.8 volts. Our E value, if we flipped it, would become positive 2.37 volts. And if we added that together, we would end up with 2 silvers plus a magnesium. Gets you 2 silvers with no charge and a magnesium with a +2 charge. And again, if you chose to flip the sign yourself, you would then take the 0.8 volts and add it to the 2.37 volts. And that will give you, as you see, the exact same voltage number as well. So again, it really is sort of a personal preference sort of choice as to whether you add or subtract. But the key is obviously don't mix those two together. Don't change the sign and subtract or anything like that. So again, like I said before, I would choose to stick with one and kind of not go back and forth. All right, so we'll stop the torture at 1:30 here. So we'll just cover a couple more things and we'll call it a day for today. All right, so tying this together, sort of our electrochemistry and sort of our thermodynamics, we're going to talk about cell potential, electrical work, and free energy. So if you remember, free energy is our good friend delta G, right? And the work that can be accomplished basically when electrons are transferred through a wire depends really on that kind of push behind those electrons are the thermodynamic force. And basically what we see is 1 joule of work is produced or required when basically 1 unit of charge goes between 2 points, like a electron traveling on a wire from the anode to the cathode. And there is a relationship between sort of our thermodynamics that we were talking about in the previous chapter and our electrochemistry here that we're talking about in this chapter. So when a cell produces current, its potential is positive and the current can be used to do work. So typically when we get a positive cell voltage, that usually indicates a spontaneous process. And we can use that spontaneous process in those electrons, like a battery or something like that, to do some type of work. And putting that together with our thermodynamics, ultimately where we get to is that the change in free energy, which if you remember, that's sort of what free energy is the energy available to do some type of work, is equal to the maximum work that we can kind of put out in sort of this electrochemistry sort of situation. So where we get to is tying together some of our thermodynamic properties with our electrochemical properties. So let's talk a little bit about some of these guys here, and we'll get to what all that is here in a sec. All right, so let's talk about what we see on this slide first. So tying together our electrochemistry and our thermodynamics is this equation here. Our delta G equals minus NFE. And this is basically E of the cell. So this guy is your cathode minus your anode, just like we were doing in the previous problems. F is a constant. F is what's known as Faraday's constant. It's 96,468, give or take. So 96,500, which is a constant. And N is the moles of electrons. And the moles of electrons is an important number because people also sometimes like to mess it up a little bit. So the moles of electrons are the total number of moles that have been transferred from your anode to your cathode. So just to illustrate what that means, we look back on a previous one there that we had an equation. We'll go here, right? So if we look back at this one that we saw earlier, when we look at each half reaction in the balanced half reaction, this equation here had 6 electrons. This equation here had 6 electrons. If you were to calculate what N was for this one, N would equal 6 only, not 12. So sometimes people want to add both of those together. But what you have to remember is those 6 electrons, for example, are being lost by the chromium, and those same 6 electrons are being gained by the cadmium. So it is basically, when you calculate N, the total number of electrons that have been moved from your anode side to your cathode side. So don't add both electrons together in each of the half reactions, which is, again, a sort of common error that sometimes people will do. So this is an equation where we could calculate delta G and figure out whether or not a reaction will be spontaneous or not. And if you remember delta G, if that ends up being negative, the reaction is spontaneous. And if delta G ends up being positive, it will be a non-spontaneous process. And what we know about delta G here and our electrochemistry is, since F and N are positive numbers, if we end up with a positive E value, we should end up with a negative delta G value. And vice versa, if we end up with a negative E value, negative and a negative will give us a positive delta G. So that's why we say when we get a cell voltage that is positive, we know it's going to be spontaneous, because when you put it into your delta G equation there, you will get a negative number, which implies that that reaction is going to be spontaneous. And vice versa, if you get a cell voltage that is negative, we know that that reaction will be non-spontaneous, because it will lead to a delta G value that is positive. Now, if you're building a galvanic cell and you get a negative voltage when you put them together, in order to fix that, you essentially just need to reverse your anode and cathode. And when you reverse your anode and cathode, you will end up with a galvanic cell that has a positive voltage. So if you're actually building a galvanic cell and end up with a negative value, you actually can reverse the two and make it into a positive one, because you're basically reversing all the reactions. So we could use this to figure out delta G. If we know delta G, we could figure out E of the cell, and vice versa. And of course, our good friend, the equilibrium constant, cannot be left out as well. We can use this equation here, our formula here, that ties together equilibrium and E of the cell. So same idea, E of the cell here would be your cathode minus anode under standard conditions. R, as you can see here, is our gas constant, and it is the 8.314 version. T is our temperature in Kelvin. N is our moles, and F is our Faraday's constant. Now, if you happen to be at 25 degrees Celsius, all three of those things become kind of like constants, and it will reduce down to one of these two equations, if you like to use this one's instead. 0.0257 divided by N times the natural log of K. And that's what you get when you kind of take 8.314 and 298 and all those numbers. Or if you're more of a classic log version kind of person, 0.0592 volts divided by N times the log, LOG, base 10 of the equilibrium constant. You don't want to worry about remembering any of these equations. You basically can just remember this equation and just put the numbers in, including at 25 degrees, and everything will come out pretty much the same. Might be slightly different depending on rounding, but everything will sort of come out the same in there. So the bottom two equations on the left are just sort of shorthand equations that are used at 25 degrees Celsius. But if you don't want to remember them, you can remember the one in the green box and just put in all the numbers and it'll come out the same. So this relates both our thermodynamics that we talked about in the last chapter and our electrochemistry together in the trifecta of death here, or triangle of death. If you know the delta G, That will allow you to figure out E of the cell, also allow you to figure out our equilibrium constant from an earlier equation from the previous chapter. If you know E of the cell, you can get to delta G and K by using one of these two equations. And obviously, if you know K, you get to E of the cell, our delta G as well. So our delta G, our E, or K are all tied together by those three equations on the right. And again, by knowing any of those things, you can figure it out. The same thing rules for this equation here. And the K value, just like before, if we have a large value of K, that should mean we should have products, which means, like we talked about in thermodynamics, that reaction is probably going to be spontaneous the way it's written, and that probably would result in a positive E value. And vice versa, if you have a small value of K, that means you're going to mainly have reactants, probably going to be a non-spontaneous process like we talked about there in thermodynamics, and that usually will result in your E value of being negative. So again, all of these sort of properties, they do sort of tie together and work together the same way as normal. And again, these are sort of the equations that tie together the two on the left there, the one in the blue circle and the one in the green box. Those are the two that really tie together both our sort of thermodynamic properties and our electrochemical properties. And like anything else, they all should sort of agree in terms of reaction being spontaneous, products being made, and so forth. Any questions on that there? Okay, I think that's probably enough torture. I appreciate you hanging in there for the lecture and stuff like that. So we'll stop here on Tuesday. Today's Thursday. That's good. So on Tuesday, we'll obviously continue on working here. Like I mentioned before, I don't know if today will be up, but maybe the next day or so, the next experiment, which is basically, I think, just more straight redox stuff, the stuff we sort of talked about in lecture and at the beginning of the lecture here today in lab. By that stuff, you probably should be able to sort of work through it. So I probably will be posting that up in the next day or so in case you want to kind of get a jump on that. A reminder that, again, the titration experiment is due next week officially. Technically, I think the buffer experiment was due a couple days ago. But like I said before, again, I know things are happening. So if you still need to kind of submit some of that stuff, you may take a ding, obviously, on lateness, but maybe better than no points at all. So everything, I think, again, for the buffer one should still be available for you to submit, even though it says it's past the due date. It will just mark it late if I'm remembering correctly. So I would probably recommend that if you are sort of in that situation. If you're not, that's very good. But in terms of the titration one, make sure that you keep up with that one. Yeah. To be honest with you, I'm trying to think. Next week we can during lab, if necessary, we could go over the oxidation one. I'll be honest with you, it's kind of straightforward, the one that's coming up, if I'm not mistaken. Um, in fact, to be honest with you, I'm not sure, but they used to do almost the first part of that experiment in Chem 50. So it might even look very familiar to you, at least the first part of it, of that experiment. So you probably can kind of go through that. The last part may be a little bit different, so we can talk about it on Tuesday more formally. So we'll do that for sure. So formally on Tuesday, if you need to, during lab time, we'll formally talk about the redox experiment. But again, like I said, you probably will be able to kind of work through most of that, I think, to begin with now for sure. So I will probably post it up there in the next day or two. But if you need to wait till Tuesday to get kind of a formal introduction on what's going on, I'll introduce it on Tuesday during lab. It won't be due next week, obviously. But like I said, if I'm not mistaken, I think almost the first part of the experiment is similar to an experiment that maybe you did in Chem 50. So at least part A of that experiment would be probably something that looks very familiar to you and stuff like that. Maybe the second and third part might be slightly different, but with the information that you have now, you probably should be able to kind of tackle some of that stuff as well. So, but just to make sure everybody's on the same page, on Tuesday, we'll officially kind of introduce that experiment during lab time on Tuesday. Other questions? Let's see. Yeah, so the pictures that they ask you to take and all that, I'm trying to think. You can incorporate them wherever you think might be appropriate. If you want to incorporate it in like the data section, you can, if you like, with your table. If you want to do that, you can put it there, or just make sure they're obviously in the report somewhere. But maybe put it in where you think it might kind of go. So maybe in that part of it. No, so I think what you're asking is like in the titration, you basically were to take like a burette reading for every pH sort of thing. And then from that, you were going to make your curve, I believe. So I don't think I need the sort of raw data in the report, if you will, but I do need the graphs of the, so you should have had to make like titration curves basically. So I need those graphs sort of properly made. And if I'm not mistaken as well, I believe on those graphs, they have you sort of identify certain parts of the graph as to what's going on. So make sure that I have the graphs and then obviously where those points are. Yeah, I don't need the raw data because I don't know. In real life, it can be a lot of points. So I'm assuming on the simulator, it's probably a lot of points as well. And maybe you have a pretty big table. So if you're asking, do you then need to kind of make like your own Excel table or something like that, or kind of turn it in and sort of put that into the report? I don't necessarily need that, but I would need obviously the graphs that you made, from that information, if that sort of makes sense. What you should do is what you should do obviously is kind of like a normal report is, for example, for that titration, you'll probably figure out maybe the volume of the equivalence point, half the volume of the equivalence point, the pKa value, those type of values. So instead of sort of that raw data of the burette reading and the pHs, you should be making perhaps some tables where you put that kind of more important information in, like the pKa values, the volume to reach the equivalence point, those type of things would be probably better. Other questions on titration report or anything I can help you with? Okay, so we're going to officially stop sort of the lecture here, and I'm going to take a little break to kind of stand up and all that good stuff. So I tell you what, if you still have some questions, maybe on titration or something like that, I'll be back on at like 2:00. So I'm going to cut this one off. That way I could post this with the recording of really just the lecture part. And if you have some questions between say 2 and 2:30, I'll be back online. So you could just come back through the same lab link, and I'll restart it around 2 after kind of stretch it a little bit. And then I'll be there until about 2:30 again in case you have some more questions or something like that. Other than that, have a nice weekend. And like I said, make sure you keep up with all this good stuff and also your projects as well. And again, if you had any issues with your projects in terms of which one was accepted, just let me know and we can work with that. All right, I'll see everybody if you still have questions in about 20 minutes until about 2:30, and then I'll be out for today, I think. All right.